So this work is on the sizing and siting of energy storage systems, considering both the TSO and DSO perspective. I probably didn't introduce myself. I'm Paola Pongiglione from University of Genova, and this work has been developed together with, in collaboration with EPFL from Lausanne. Going to the outline of the presentation, I will start from the introduction and the goals.
Paola, put FF5 to put full screen.
Sorry. Sorry. Okay. So after the introduction on our goals, I will present the formulation that we developed. So focusing mainly on the linearized formulation that we used, the modeling of the storage devices and on the decision problem. Then I'll describe the test cases and the simulation scenarios that we built. That is a tentative demonstration of the great effectiveness of the formulation. And then I'll go through the results and the conclusion of the work. So as most of you mentioned today, we tried to target both the concerns from the TSO and the DSO. So the need for reserve on the transmission level, and at the same time, the need for distributed regulation in the distribution level due to the increased distribution, the increased penetration of distributed generation. What we try to do is to plan the optimal installation of energy storage systems, which can be very useful to deal with both needs. The research question, as we said, is try to develop an efficient integration of all these needs and take into account multiple services at the same time, considering both the TSO perspective and the DSO perspective. So considering both voltage levels, not performing only an horizontal siting, but considering two different voltage levels. The grid model that we use is a linearized power flow, in order to maintain the tractability of the problem, since it's going to be computationally relevant. And the model that we use derives the voltage magnitudes, the line currents, and the slack power with respect to the nodal injections and the slack voltage. So this allows us to optimize the local injections that are supplied by the batteries, and at the same time taking into account the slack voltage regulation and the tap changers. I don't know why it switches automatically. The sensitivity coefficients are computed on the day-ahead forecasts, and then the optimization is performed using the real-time profiles. The energy storage is modeled in the simplest ways possible. So there isn't an explicit formulation of the size and on the power size and on the energy capacity, but we simply consider the nodal injections in time, and at the end of the optimization, we compute the maximum power that is required and the maximum state of energy that is reached on a daily horizon, so that we impose every day to reach the same state of energy that was given at the beginning. In order to preserve convexity, we model the efficiency of the batteries by adding a resistive line in the grid model at all the nodes where the batteries can be installed. So this retains the convexity of the problem and doesn't increase the complexity, but it takes into account the losses due to charge and discharge. So recapping the strategy, we have the PV and load forecasts that are performed on the day ahead. Based on this day ahead forecast, we have a unit commitment for the traditional power plants on the transmission network. Then we compute the sensitivity coefficients, and finally we go on the optimization in real time using the actual realization of the forecast we used. The objective is to minimize both the cost of the traditional generation, the traditional reserve that is activated, so from the synchronous generators, and at the same time using the minimum, installing the minimum quantities of energy storage system. The problem is subject to a constraint on the state of energy, to limits on voltages and line ampacities, and to the continuity constraint between the two networks, considering also the limits for traditional reserve. The case study that we used is a combination of two networks. For the H voltage, we consider the IEEE 9 bus systems, and for the medium voltage, we consider the SIGRE benchmark network, considering 3 plants on the transmission networks and a high photovoltaic penetration in the medium voltage grid, not only in the grid that is modeled explicitly, but also in the load A that is representing another medium voltage grid. The PV penetration is assumed to be strong in order to have some mild reverse power flow conditions. The load flow models are modeled separately, but we impose a continuity constraint between the MV and the HV grid, so that the active and reactive power are consistent, and also the voltage magnitude, while including the tap changer regulation. The simulation scenarios that we use are 20 days for now in order to maintain tractability of the problem. So we consider 4 daily case studies, considering the 4 seasons, and the 5 different days for each season that are obtained by clustering real measurement from the EPFL campus, both for the PV and demand. We use point prediction with a non-parametric KNN model, and we derive the forecast for the PV by considering the weather predictions. The same profiles are derived not only for the MV grid that is modeled in detail, but also for the other grids. The costs that to consider are, let's say, optimistic. So the reserve is considered at 50 euros per megawatt, which is near the average spot price. So it's pretty conservative for the simulation we are performing, but also the battery costs are assumed to be lower in the future, considering the perspective of higher investment on this technology. And the reactive regulation is supplied for free. So the results of the allocation show that this technique is effective on all the aims that we targeted. So the main problem is voltage regulation, and we can see that all the available technologies are strongly used. Both the OLTCs are activated by the system, but also the batteries are required to supply often reactive regulation, and as well the traditional power plants. And we can see that the batteries are often have a higher power rating with respect to their active power capacity, which means that since we consider different costs for the converter and the energy capacity of the buses, there is the option to oversize the converters in order to be able to supply reactive regulation. It is also noted that we verified ex post in this specific case that even if we allowed the PVs to supply reactive regulation, in this specific case, it wouldn't reduce much the total storage system to be installed, since those that supply the highest contributions also have a high power requirement. We can see here some screenshot of the constraints that are verified. So on the bottom left, we can see that the day ahead forecast is respected. So many different technologies can be used so in order to match the day-ahead profile with the actual sum of all the powers involved. On the top right, we can see that the voltage magnitudes that showed a lot of problems of over voltages are taken back to the imposed limits, that is 5%. And also for the currents, we can see in the bottom that actually this was not critical in the simulations. We assumed that there were just very mild violations, and they're respected. Also, we performed a comparison with respect to traditional regulations. So we tried to simulate the same test case by using only the traditional plans. And the first thing is that the scenario was infeasible. So we had to relax the constraint on voltage from 5% tolerance to 7% tolerance in order to make it feasible. And also the price is anyway higher. So we can see that in this case, storage is not only cost competitive, but also more efficient than traditional regulations. And if we think that voltage regulation might be even remunerated in the future, this could be even more convenient. In order to sum up, we can say that the algorithm we proposed manages to take into account both the TSO and DSO needs, providing different grid services and helping for grid control also in the distribution network. And the simulation is tractable using some linearized models, but verifying that the approximation is still acceptable. And we use several scenarios in order to capture the uncertainty that is related to forecast of PV and demand. The storage systems are allocated mostly in the medium voltage in order to provide both reserve while mitigating the voltage problems that are related to PV penetration. And it results to be also cheaper than activating the traditional reserve on a 20 years horizon. So future developments of this work will include other technologies, and the actual strongest point of this formulation is that it can be used for really several different scopes, and is very flexible with respect to the needs that can be considered. And this will allow to investigate the best policies to foster the installation. Yeah.
No, okay, just conclude.
Okay. Oh, it's finished.
Okay, thank you a lot, Paola.
Yeah.
Unfortunately, we had some problems, but we are recovering.
Sorry.
We have any open question from the floor? We have one about the modeling of, well, we have two that we can be coupled. And basically the idea to use the efficiency of the battery using series resistance. And Zhao was pointing out about the use of series and shunt resistance. Done about which resistance did you use for this model? Okay,
so the resistance can be should actually be validated. The original idea was to make a second iteration of the code, actually using the resistance that is related to the rating of the batteries that is installed, because it is actually related to the capacity of the battery. We didn't do it yet, but this should not be so significant on a planning horizon as we simulated. It is certainly related to the actual size, but it should be more relevant on a control strategy rather than planning. But there are some references on the technique that we used.
That's fine. Okay.
That's the same for both. Thank you.
Okay, now we have to move on because we are short in time. It's nice to see that we are starting to study all the services together.